Hey guys, so in today's video we're going to discuss some questions that have come from the JEE Main Examination from the Vernier Calipers. So right in front of us we've got the first question, so let's read it. In a Vernier Calipers, 10 divisions of a vernier scale is equal to 9 divisions of the main scale. When both jaws of the Vernier Calipers touch each other, the zero of the vernier scale is shifted to the left of the zero of the main scale. Okay, so this is talking about the error. And the fourth vernier scale division exactly coincides with the main scale reading. One main scale division is equal to 1 millimeter. Okay, that's basic stuff. While measuring the diameter of a spherical body, the body is held between two jaws. It is now observed that the zero of the vernier scale lies between 30 and 31 divisions. The zero of the vernier scale lies between 30 and 31 of the main scale. And the sixth vernier scale division exactly coincides with the main scale reading. So they want us to find the diameter of the spherical body. So let's, consolidate all of the pieces of information they gave us. So they gave us that 10 VSD is 9 MSD. They also gave us that 1 MSD is 1 millimeter. And these are the basic conditions that we've discussed in the previous videos. So we can just directly say that the least count here is 0.01 centimeters. Now, the next thing they've talked about right here is the error of the vernier calipers. So they gave us this right here. The zero of the vernier scale is shifted to the left of the zero of the main scale. So let's just draw it right here. Let's just say this is the zero of the main scale. I'm just going to write MS here for main scale. And the vernier zero shifted to the left. So that means the vernier zero is somewhere here. This is the vernier scale. And they also told us that the fourth vernier scale division exactly coincides with the main scale reading. So, right here, we can say that, obviously, right here we would have negative 0.1, as we've discussed in the previous video. This is a negative error. So let's take a look. So the main scale reading is negative 0.1 centimeters. And the vernier scale reading, they've told us that the fourth vernier scale division exactly coincides with the main scale reading. So that means the vernier coincidence is 4 times the least count, which is 0.01 centimeters. So with this we get that the vernier scale reading is 0.04 centimeters. And when you're finding the final reading, which is the sum of the MSR and VSR, we get negative 0.1 plus 0.04, which is negative 0.06 centimeters. So this is the initial reading. And that is our error in this case. Now, they told us, after we put the object between the two jaws, they told us that the zero of the vernier scale lies between 30 and 31 divisions. So if this is the main scale, and this is 30 and 31, these are in millimeters, by the way. So then what we would get, the vernier scale zero lies in between. So that means our main scale reading is 30 millimeters or 3 centimeters. And they also told us that the sixth vernier scale division exactly coincides with the main scale reading. So with that, we can easily say something here. So obviously vernier scale reading is the vernier coincidence times the least count. So vernier coincidence is 6 times 0.01, which is 0.06. And the final reading is equal to the sum of both of them. So with that, we can say that the main scale reading is 3.06 centimeters. And this is R2, the final reading, and this is R1, the initial reading. Now, all we gotta do here is, so we know that the actual dimension D, or in this case the diameter D, is R2 minus R1, as we've discussed in a previous video. So 3.06 centimeters minus of negative 0.06 centimeters, which is 3.12 centimeters. So that's our reading in this case. This is the diameter of the spherical body. So here's the next question. Let's read it. The least count of the main scale of a Vernier calipers is 1 millimeter. Its vernier scale is divided into 10 divisions and coincide with 9 divisions of the main scale. When the jaws are touching each other, the 7th division of the vernier scale coincides with a division of the main scale, and the 0 of the vernier scale is lying right of the 0 of the main scale. When this vernier is used to measure the length of a cylinder, the 0 of the vernier scale is between 3.1 and 3.2 centimeters, and the 4th vernier scale division coincides with the main scale division. The length of the cylinder is. Okay, so this is pretty much the same, almost the same as the previous question. The only difference that we can see here is the units that they've given us, and also the fact that the vernier 0 is lying to the right of the main scale 0. So let's do this question. Obviously, the beginning stuff, they've stated the obvious. We know that the least count of the main scale is 1 millimeter, and we also know that 10 divisions coincide with 9 divisions. They stated the obvious. So let's get to the question. So they first told us that the second important thing they told us is about the vernier 0 and the main 0 when the jaws are touching. So that's the main scale, and this is the vernier scale. And they said that let's just say that this is the main scale 0, and the vernier scale 0 is lying to the right. So this is already showing some positive reading, and hence we call this a positive error. And so here the error is usually just the vernier coincidence times the least count, which is 7 in this case, times 0.01. And that is, 0.07 centimeters. So that's R1, or our positive error in this case. Now, when the vernier is used to measure something, or in this case, length of the cylinder, the 0 of the vernier scale is between 3.1 and 3.2 centimeters. So let's just say this is 3.1 and this is 3.2. Our vernier 0 is somewhere in between. So no matter which two things it's between, whichever one is on this side of the vernier 0, that is our main scale reading. So in this case, our main scale reading is 3.1 centimeters. And they also said that the 4th vernier scale division coincides with the main scale division. So they gave us the vernier coincidence, which is 4. And so our VSR is 4 times 0.01, which is 0.04. And we finally get that the reading R2 is 3.14 centimeters. Now, obviously they asked us the length of the cylinder, so we can write L is equal to R2 minus R1, which is 3.14 minus 0.07, which is 3.07 centimeters. So this is the final not the final reading. Actually, when they ask you the reading, this would be the reading. But the actual length would be this. That's our actual length of the cylinder. So this question here and this question here are pretty much the same. The only difference is the fact that here they've given us a positive error, and in this question they gave us a negative error. So there would be a difference in calculation in that point. But other than that, these two questions are practically the same. Here's the next question. So let's read it. In a vernier calipers, when both jaws are touching each other, the zero of the vernier scale shifts towards the left, and its fourth division coincides exactly with a certain division on the main scale. If 50 vernier scale divisions are equal to 49 main scale divisions, and the zero error in the instrument is 0.04 millimeters, then how many main scale divisions are there in 1 centimeter? So let's, in this question, they've given us some pieces of information. Each are equally important, but we have to first start out with something in order to do the question. Like, just pick one piece of information that's important. And that is this. We'll first start out with that highlighted piece of information. So let's see. They told us that 50 vernier scale divisions is equal to 49 main scale divisions. So 1 VSD is 49 over 50 MSD. So that's what they told us. Now, we need to take this one step ahead, so we need to find the least count. The least count in this case would be MSD minus VSD. Not only in this case, in every case. This is true in every case. But here what we gotta do is just subtract 1 minus 49 over 50 MSD. So the least count is 1 over 50 MSD. So that's what we got initially. Now, they also told us some other things in this question which are pretty important, but they also mean the same thing. They told us when both jaws touch each other, the zero shifts to the left, and the fourth division coincides exactly with a certain division on the main scale. That's one thing they told us. And the second thing they told us is the zero error in the instrument is 0.04 millimeters. So these two pieces of information, the blue highlighted one and the green highlighted one, mean the same thing. They're talking about the same thing, which is the reading of the instrument before anything is put inside, basically when the jaws are closed. So they told us that the zero error is 0.04 millimeters. So we're talking about the error here, and they told us that it's 0.04 millimeters. And they also told us that the fourth division coincides exactly with a certain division on the main scale when the two jaws touch each other. So that would be the zero error, right? So it would be 4 times the least count, which is 1 over 50 MSD. Now we just have to find out how much 1 MSD is. That's basically what we gotta do. So this is 4 over 100, which is equal to 4 over 50 MSD. So 1 MSD is equal to half a millimeter. So that's what we'll get here. Now they want us to find the main objective of this question is how many main scale divisions are there in 1 centimeter? That's what we need to find. So let's just say that there are y main scale divisions in 1 centimeter. Just taking that as a variable. So y times half a millimeter should be equal to 1 centimeter, right? So let's just say that half a millimeter is that. In centimeters. I converted everything to centimeters. So this is times y is equal to 1. And then when you do simple math, we'll get y is equal to 20. So there are 20 main scale divisions in 1 centimeter in this Vernier calipers. So yeah, that would be our answer right here, 20. So now that we finished that previous question, I just want to give a quick note about the previous question, as well as some that are similar to that but have a small difference in it, and how to attempt those questions. So in the previous question, we had that 49 MSD coincide with 50 VSD, right? So because of this, we also used the formula that least count is equal to MSD minus VSD, right? That's what we used in the previous question, this formula right here. However, this can only be applicable in a certain case. Like, for example, we used this formula right here when 9 MSD were coinciding with 10 VSD. And similarly, we could use this in all the cases where n MSD are coinciding with n plus 1 VSD. So we can use this formula right here when this happens, when n MSD are coinciding with n plus 1 VSD. That's when we can use this formula right here directly as the least count. However, in some other cases, for example, let's say 9 MSD were coinciding with 11 VSD or something like that, we have to try something different and, draw it out to check the least count. So with those, we're going to have to approach the question in a different way rather than directly using a formula. In fact, we can also directly find the least count in this case by drawing it out. However, it's a waste of time when you have this case right here and you can directly use it. But we'll also prove the least count in this case as well. So let's get started. I'm going to take, just to prove this one right here, I'm going to take the simple example that we always take, which is 9 MSD coinciding with 10 VSD. So here's the drawn out scale right here. So obviously we can see that there are 9 main scale divisions coinciding with 10 Vernier scale divisions. And this is in the form of n and n plus 1. So now that we've got that, and we know that each MSD, this is a regular Vernier scale, right? So there are 10 MSDs in 1 centimeter. So that means 1 MSD is obviously 1 millimeter. And so till here, we've got 9 millimeters of length. So that means 10 VSD should be equal to 9 millimeters. So from that, obviously we can say that 1 VSD is equal to 9 over 10 MSD. We've derived all of these in previous videos. So after we get that, all we have to do is write down what each Vernier scale division corresponds to. So, these numbers up here, they represent the millimeters. So this is 1 millimeter, 2 millimeters, 3 millimeters, and so on. But these are quite different, so we're going to have to check that. Let's use a different color. Okay. So the first vernier scale division is 0.9. And these are in millimeters, by the way, because here, when 9 over 10 MSD is equal to 1 VSD, that means each one is 9 over 10 millimeters, or 0.9 millimeter. So anyway, let's continue. This is 1.8, 2.7 millimeters, 3.6, 4.5, 5.4, 6.3, 7.2, and 8.1. And the final one is 9. So as we can see, at the end of the 10 vernier scale divisions, we do get 9 millimeters. So, we know that they're equal. So now let's check, as I've mentioned before, the least count represents the least distance between a main scale division and a vernier scale division. So let's check what the least distance between each of the corresponding main scale division and vernier scale division is. So let's see. This one is 0.9 and this is 1. So the corresponding least distance would be 0.1. This is 0.8 and this is 2. Corresponding least distance would be 0.2. 2.7 and 3. Corresponding least distance would be 3 minus 2.7, which is 0.3. This is 3.6 and that's 4. So the corresponding least distance would be 0.4. This is 4.5 and this is 5. So this would be 0.5. Now from here onwards, from 5.4 onwards, we're going to have to check from backwards, because from here, the distances are decreasing with respect to the one before. So if we check 5.4, that's 0.4 away from 5. So this distance again would be 0.4. When we check 6.3 with 6, again 0.3. 7.2 with 7, that's 0.2. 8.1 with 8, that is 0.1. And 9 with 9, that's 0. So the least distance between between a main scale division and a vernier scale division, other than 0, is 0.1 millimeters. And hence, the least count here is 0.1 millimeters, or 0.01 centimeters. So that's how we got the least count in this case, by drawing it out. Here, since the least count formula in this case and also what we got here are the same, we can directly write that the least count is the main scale division minus the vernier scale division. This case, or this formula for that, is true for all possibilities where n MSD are coinciding with n plus 1 VSD. So with that, we can conclude the first part. However, there's still a second part where, this case is not there. So for that, let's take a simple example of 7 MSD coinciding with 9 VSD. So here's the scale regarding that. This part, it might not be evenly split, but I've tried to draw it according to the values, so this is how accurate I can draw it, okay? So as we know, I'm going to take the general case where 1 MSD is equal to 1 millimeter, just for our convenience. So yeah, let's see. If 1 MSD is 1 millimeter, then that would mean till here is 7 millimeters, right? Now let's, find out two values. One is the least count using the number line and finding the least distance between two divisions. And the other one is by using this formula. And we'll compare those two values. So let's first find the least count using the formula. So this is, we know that 1 MSD is 1 millimeter, and here is 7 millimeters. So 7 millimeters is equal to 9 MSD. Sorry, this is VSD. 9 VSD. So then we get 1 VSD is equal to 7 over 9 millimeters. And when we're finding the least count according to this, which isn't really the least count, so I can't really call it that. But anyway, this is the MSD minus the VSD. And then that would be 2 over 9 millimeters. According to what we got, 2 over 9 is the least count. However, that's not true, and you'll see why also. So, let's see. 2 over 9 millimeters. Okay. Oh, also another note. This value right here, this value, MSD minus VSD. In the case of n MSD coinciding with n plus 1 VSD, it's called the least count, but generally this value of MSD minus VSD is called the Vernier constant. So this is actually called the Vernier constant. I forgot to mention that before. So now for my satisfaction, we can call this the VC rather than the LC, because it isn't the LC. So yeah, we got the Vernier constant, or the formula least count, as 2 by 9 millimeters. Now let's find the least count using the number line. So let's first check what these values represent. These values. So obviously, I'm gonna write these in fractions, by the way. So 1 MSD is 7 over 9 millimeters, so this is 7 over 9. This is 14 over 9. This is 21 over 9. 28 over 9. 35 over 9. 42 over 9. 49 over 9. 56 over 9, and 63 over 9. 63 over 9 millimeters is the same thing as 7 millimeters, so we know that these two are coinciding. Just a way to check if your values are correct or not. Now, let's, compare and contrast these differences between them and check which one has the least. So, just for our convenience, I'm going to write all of these values in, fractions with denominators of 9. So I'm just going to write that real quick. This is 9 over 9, 18 over 9, 27 over 9, 45 over 9, 54 over 9, and 63 over 9. So now that we've written those, we can finally compare the differences. So let's see. So between 7 over 9 and 9 over 9, we got 2 over 9. Okay. 14 over 9 and 18 over 9, that's 4 over 9. 21 and 27, that's 6 over 9. So far it seems to be increasing. 28 and 27. Once again, we're trying to look at the least, not the most. Basically from here till this, the distance between the divisions is increasing. However, when we're looking at these distances,
We just have to check the least between them, right? Actually, here also, we can check the least. Even though this is 27 here, it's 18 on this side. So actually, instead of 6/9, we should write this as 3/9. Now, let's continue. 28/9 and 27/9. That would be 1/9. This is 35/9 and 36/9. That's 1/9. 42/9 and 45/9, or 36/9. Which one seems the least? Obviously, that would be 45/9, so we'd get 3/9 again. 49, and then we got to compare between 45 and 54. Either way, this one would be 0, but either way, we get that our least is 1/9. So, at the end, we get that the least count in this case is 1/9 millimeters. So here we got the Vernier constant, or the formula least count, as 2/9 millimeters. However, when we're drawing the diagram, we get the least count as 1/9 millimeters. So you gotta be careful with these types of cases where, the number of MSD coinciding with the number of VSDs is not in this format right here. So when we're getting something that's not in this format, we gotta be careful and draw the diagram and check the values so that you get the actual least count. So that's just what I wanted to mention right there. Forgot to mention it in the previous video, so I mentioned it now. So here's the next question. Let's read it. In a Vernier calipers, each centimeter on the main scale is divided into 20 equal parts. Each centimeter is divided into 20 equal parts. If 10 Vernier scale divisions coincide with 9 main scale divisions, then the value of the Vernier constant will be. So let's take a look at this. Here, since the okay, so they told us that each centimeter on the main scale is divided into 20 equal parts. So that means that each centimeter, which is 1 centimeter is divided into 20 parts. So that means that there are 20 MSD. 20 MSD is equal to 1 centimeter, and so 1 MSD is equal to 1/20 centimeters. And they told us that the 10th Vernier scale division, so 10 VSD, is equal to 9 MSD, the usual. And they also, from this, we can obviously say that the least count is 1/10 MSD. Now, from this, plugging in 1 MSD here, we'll get that the least count is equal to 1/200 MSD. Sorry, not MSD, centimeters. Which is basically 0.005 centimeters. And obviously from this, as we've discussed before, when the number of Vernier scale divisions coinciding with the number of main scale divisions are in the form of n+1 and n, when they're in this form, the Vernier constant is the same thing as the least count. That we can directly find by MSD minus VSD. That's what I meant. So, in this case, yes, the Vernier constant is always the MSD minus the VSD, but since in this case, n+1 and n is the form of the number of Vernier scale divisions coinciding with the number of main scale divisions, we can say that the Vernier constant is also the least count, just in this case. So right here,
when we're finding the Vernier constant, this would be our answer. But they asked it in a different unit, which is millimeters. We gotta change it according to that. So this would be 5 times 10 to the power of minus 2 millimeters. So that's our Vernier constant.